Concrete is everywhere. Beneath our feet, above our heads, inside buildings, bridges, tunnels, dams, and entire cities. It is the most widely used construction material on Earth, and at the same time, one of the least understood. Most people believe concrete is simply cement mixed with sand and water. In reality, concrete is a carefully engineered chemical and physical material whose creation begins long before it ever reaches a mixer or a construction site. To truly understand how concrete is made, you must first understand cement. Concrete cannot exist without cement. Cement is the active binding component that reacts with water, locks aggregates together, and gradually transforms a fluid mixture into artificial stone. And cement production is one of the most demanding industrial processes in the world, involving extreme temperatures, controlled chemistry, and irreversible transformations. What makes concrete so unique is the fact that it does not harden by drying. It hardens through a chemical reaction. Water does not disappear. It activates a process that can continue for weeks, months, and even years. Every mistake made during cement production, aggregate selection, water proportioning, or curing becomes permanently embedded in the internal structure of the concrete. Concrete remembers everything. The process begins in quarries. Limestone, clay, and other minerals are extracted, crushed, and chemically analyzed. At this stage, the future quality of the concrete is already being decided. Concrete may look solid on the surface, but its true performance is determined at the microscopic level. A structure can appear perfect for years while slowly developing internal weaknesses that only reveal themselves later. From the quarry, raw materials are transported to cement plants, where they enter rotary kilns operating at temperatures approaching 1450 degrees Celsius. At these temperatures, chemical reactions occur that rarely happen naturally. The result is clinker, a semi-finished material without which modern concrete could not exist. Clinker gives concrete its ability to harden underwater and achieve extraordinary strength. Only after cement is produced does it become part of concrete. Cement is combined with aggregates, water, and chemical admixtures. And here lies a critical paradox. Concrete needs water, but too much water permanently weakens it. The strongest concrete is not the most fluid one. It is the one in which every drop of water has a precise purpose. In this video, we will follow the entire process step by step, without simplifications and without repetition. From raw material extraction through cement production to concrete mixing, transport, placement, and curing. Because only by understanding the full process can you see why concrete is not just a mixture, but one of the greatest achievements of material engineering. The production of concrete truly begins with cement, and cement begins with raw materials that appear deceptively simple. The primary ingredient is limestone, supported by clay, marl, or shale. These materials are not chosen at random. Their chemical composition directly determines how the cement will behave, how fast it sets, how strong it becomes, and how durable it remains over decades. In quarries, the raw materials are extracted and initially crushed. From the very first stage, their chemical composition is continuously monitored. A cement plant does not need just any limestone. It needs limestone with precisely controlled proportions of calcium oxide, silica, alumina, and iron oxide. Even small deviations can result in cement that sets too quickly, too slowly, or develops long-term structural weaknesses. The crushed materials are then finely ground into what is known as raw meal. This powder must be chemically uniform throughout its entire volume. Modern cement plants constantly adjust the composition in real time, ensuring that the mixture entering the kiln meets exact specifications. At this point, the process is already more chemistry than construction. The heart of cement production is the rotary kiln. These massive steel cylinders rotate slowly while the material inside moves forward through increasing temperatures. As the raw meal progresses deeper into the kiln, temperatures rise to approximately 1450 degrees Celsius. Here, the process is no longer simple heating. Limestone decomposes, releasing carbon dioxide, and the remaining components recombine into entirely new mineral phases. The result of this transformation is clinker, hard, dark nodules that form the core of cement. Clinker is not yet cement, but it contains the minerals that will later react with water and create concrete's strength. This stage is the most energy-intensive part of the entire process, and the main reason cement production contributes significantly to global CO2 emissions. Once the clinker leaves the kiln, it must be cooled rapidly. This is not done for convenience, but for quality. Rapid cooling locks the mineral structure into an optimal configuration. Slow cooling would allow unwanted crystal growth, reducing strength and making the cement less predictable during hydration. Only after cooling is the clinker ground into a fine powder. During this final grinding step, a small amount of gypsum is added. Gypsum plays a crucial role. It controls the setting time of cement. Without it, cement would react with water almost instantly, making practical concrete work impossible. Gypsum provides the necessary working time for mixing, transporting, placing, and compacting concrete. The result is cement, a fine gray powder that appears simple but is chemically active and highly engineered. The moment cement meets water, it begins a chain of reactions that cannot be stopped. These reactions are what ultimately turn liquid concrete into solid stone. It is important to understand that cement is not a single universal product. Different types of cement are designed for different applications, environments, and durability requirements. The choice of cement alone can determine whether concrete lasts decades or generations. Once cement exists, concrete is still not complete. Cement is only the binder, the chemically active ingredient that holds everything together. The real mass and strength of concrete come from aggregates. This is where many people misunderstand concrete. Aggregates are not filler. They form the structural skeleton of the material and largely determine its mechanical performance. Aggregates typically make up 60 to 80% of concrete by volume. Concrete carries loads primarily through contact between aggregate particles, while the cement paste bonds and stabilizes them. That is why the quality, shape, size, and grading of aggregates are absolutely critical. Poor aggregate selection cannot be compensated for by adding more cement. Aggregates are carefully graded into different size fractions. Fine particles fill the voids between larger ones, while coarse particles carry the main loads. A well-designed grading curve minimizes empty spaces, reduces the amount of cement and water required, and increases final strength and durability. Poor grading leads to excess paste, higher shrinkage, and long-term cracking. The type of aggregate is just as important as its size. Granite, basalt, limestone, and river gravel behave differently inside concrete. Some rock types are extremely hard and stable. Others can slowly react with the alkaline environment created by cement. These reactions may take years to become visible, causing internal expansion and cracking long after the structure appears complete. That is why aggregates are laboratory tested before being approved for use. Water is the next critical component, and also the most dangerous one. Concrete cannot exist without water, but excess water permanently weakens it. Only part of the water added to concrete participates in chemical hydration. The rest exists solely to make the mixture workable. As concrete hardens, excess water leaves behind microscopic pores. Each pore reduces strength and durability. This makes the water-to-cement ratio one of the most important parameters in concrete technology. Small changes in this ratio can cause massive differences in strength. More water improves workability but reduces durability. Less water increases strength but makes placement more difficult. In the past, this was a hard trade-off. Modern concrete solves it with chemistry. Chemical admixtures are the invisible drivers of modern concrete performance. Plasticizers and superplasticizers allow concrete to remain fluid while using much less water. Set accelerators and retarders control how quickly concrete hardens. Air entraining agents improve freeze-thaw resistance. Supplementary cementitious materials, such as fly ash or slag, refine the microstructure and improve long-term durability. At this stage, concrete is no longer a simple mixture. It becomes a chemically active system where every component affects hydration, shrinkage, strength development, and long-term performance. That is why modern concrete mixes are designed in laboratories, not improvised on construction sites. Once the mix design is finalized, the process moves into a critical phase where theory meets reality: mixing, transport, and placement, while chemical reactions are already underway. Once the concrete mix design is finalized, the process enters the phase where precision becomes non-negotiable. Mixing concrete is not simply about blending materials together. It is about creating a uniform, repeatable material where every portion of the mix has the same properties, strength potential, and durability. In modern batching plants, cement, aggregates, water, and chemical admixtures are dosed with high accuracy. These are not approximate volumes or rough estimates. Quantities are weighed, monitored, and adjusted continuously. The order in which materials are introduced, the type of mixer, and the duration of mixing all directly influence the internal structure of the concrete. Too little mixing leads to weak zones and uneven performance. Too much mixing can cause overheating, loss of workability, or unwanted air entrainment. The moment water comes into sustained contact with cement, hydration begins. From that instant, concrete enters a time-dependent process that cannot be paused or reversed. Transport, therefore, becomes a controlled race against chemistry. Concrete must reach the construction site, be placed and compacted within a defined time window. During transport, truck mixers rotate the drums slowly to prevent segregation, ensuring that aggregates do not separate from the cement paste. One of the most damaging practices in concrete construction is adding water on site to improve workability. While this may make placement easier, it permanently increases porosity and reduces strength. Concrete appears cooperative in the fresh state, but the consequences of excess water emerge later as cracking, surface dusting, reduced durability, and premature deterioration. After placement, concrete must be compacted properly. This is not an aesthetic step. Compaction removes trapped air, allowing the mix to fully occupy the formwork and achieve its intended density. Air voids left inside hardened concrete act as stress concentrators and dramatically reduce load-bearing capacity. Proper vibration ensures that concrete performs as designed, not merely as it appears. At this stage, concrete still looks like a wet, shapeless mass, yet internally irreversible reactions are already progressing. The internal framework that will define strength, stiffness, and durability is forming molecule by molecule. What happens next will determine whether concrete reaches its full potential or fails long before its time. Once concrete has been placed and compacted, many people assume the job is finished. In reality, this is where the most important phase begins. Concrete does not harden by drying. It hardens through a chemical reaction that requires water and time. If either is missing, concrete will never reach its intended strength or durability. This phase is known as curing. During curing, cement particles react with water and form a dense network of microscopic crystals. These crystals grow gradually, filling the space between aggregate particles and locking the structure together. This process does not happen instantly. It unfolds over days, weeks, and in some cases, years. The greatest enemy of young concrete is premature drying. Wind, high temperatures, or direct sunlight can cause water to evaporate faster than hydration reactions can occur. When that happens, hydration stops early. The concrete may look solid, but internally it remains incomplete and permanently weakened. That is why proper curing, through water spraying, covering, or curing compounds, is not optional. It is a structural necessity. Concrete strength is commonly evaluated after 28 days. This does not mean concrete stops hardening at that point. It simply means it has reached a level of strength suitable for standard use. In reality, hydration continues as long as moisture is present. Well-cured concrete can continue gaining strength and durability for decades, becoming denser and more resistant over time. This is where the central truth about concrete becomes clear. Concrete is not forgiving. Every decision made during raw material selection, cement production, mix design, water proportioning, mixing, transport, placement, and curing is permanently recorded in its internal structure. Errors may remain invisible for years, only to reveal themselves later through cracking, surface degradation, or loss of load-bearing capacity. But when every step is done correctly, concrete becomes one of the most durable materials humans have ever created. From quarry stone to rotary kilns at 1450 degrees Celsius, from precise mix design to slow chemical hardening on site, each stage contributes to a final material capable of lasting generations. Concrete is not created in a moment. It is created through controlled chemistry over time. And that is why it forms the foundation of the modern world. Not because it is simple or cheap, but because when understood and executed correctly, it endures.